Hi, my name is Steph Nelson. I'm an application engineer for Siemens. Thank you for joining me today, and I am going to be talking about how we can describe specific sounds with words, and then once we have those words, we know what sound quality metrics we can use to analyze them. So my goal for today is if you are an NVH engineer and you're in the lab and you hear a product suddenly go awry, you don't know why, what's wrong, or how to analyze it, because you can analyze it a ton of different ways. We're going to build the vocabulary that will help you figure out what metrics you should be using to analyze them, and then we'll go through what the different sounds are and how you can do that. I will be working off of this community article today called Describing Sounds with Words. I'm going to be looking mostly as a cheat sheet off of what words can be used, and this is designed to be interactive, so you can be playing at home as we go through how to describe these sounds. So my first one, I have a sound for you here. So how would you describe this sound? I'm going to play it one more time. We would describe a click as something like a pop, or something very quick and dies off very quickly. Broadband noise would be something very similar to like white noise. It's very spread out across all frequencies. It's going to sound like a shh. And so typically it would be between these two answers, and I think because it's so tonal, you can almost hear it say hoot. We'll try it one more time. See if you can hear it. That's a scary sound on a product. You probably don't want to be hearing or exciting that. So if I go quickly to my cheat sheet, I'm going to scroll down to hoot and see what we can use to analyze it. So hoots, we usually look at something natural frequency and resonance. And I'll describe what those are in just a second. So I have TestLab open with that exact sound. Come in here to my noises, and here's my hoot. This is the same sound we heard just a second ago. I'm going to add this to the input basket, and we're going to try to figure out where that really tonal hoot sound is coming from. So I'm going to go to processing and get rid of that, just put a spectrum average on. I'd like to keep my resolution at 1 Hertz so that I can see all my frequencies. All of this looks good, and I can click run. And if I go to my active analysis section, I can look at my auto power. And let's zoom out real quick. If I'm just kind of looking around, it doesn't seem like there's any super obvious hoots or peaks that stick above the rest of the data, but we heard one. There's kind of one over here. I'll zoom in around this area. It doesn't look like it's super sharp, but it's probably sharp enough. And one thing we can do as a sanity check is I can actually make this signal again just to compare it. So this is at around 610 Hertz. So I'm going to make a sine wave, a pressure wave, because this is a sound wave. I'm going to make it at about 75 dB, and we'll let it run for about 10 seconds. And for the frequency, I'm going to set it to that 610 Hertz-ish, where that peak is. I will call this new one 610 Hertz. I should probably add Hertz. And then I'm going to connect this to my spectrum average. And I'm going to make sure that I hit save because I want to be able to play back this time signal later. So I'm going to reject this and I'll run it again now that I have a new signal. Okay, and I will hit accept. And now if I go to my desktop, I could go to post-processing, and I'm going to be using Audio Replay in TestLab to play these back. If you want to use Audio Replay, it requires no tokens. You can go to Add-ins, Audio Replay, and I'm up here in the Audio Replay, but I also just have the play button down here. So let's listen to the two files. So here's that first one, that hoot. I'm going to play it really quick. And here's the tone we generated. So pretty similar. We can say that that hoot is pretty much this tone we generated here that stuck out of the data. Now once we have that data, now we know that we're really aiming to reduce that 610 hertz sound. That 610 hertz sound is probably tonal, so it's generated from something like a natural frequency. So if you have a guitar string, for example, you imagine you pluck a guitar string, it's going to vibrate at its natural frequency, which is a property of the stiffness and the mass of that guitar string. Now, when it's vibrating and it's really resonating, we have a sharp peak. That peak occurs at a specific note or frequency. In our case, that was the 610 hertz. Now, if I was the engineer who was tackling this problem, my goal would be to either damp that peak so it's not nearly as noticeable, kind of like the equivalent of putting your finger on a guitar string and plucking it. You can still hear the tone, but it's definitely not as loud or as vibrant as it normally is when it's able to just resonate on its own. Or my plot would be to eliminate it altogether. So in that hoot example, it sounded like air passing over an opening. So I might design something like a Helmholtz resonator to eliminate that particular tone. So that's an example of what we would do if we had something like a hoot. So let's see if we could describe this sound. I'll play it one more time. Now, I would describe this as a click. I would not describe it as a chirp or a clatter or lugging. We have some description of those later. But you can see in my graph here, this is the data. A click is something that's really transient. It's something that dies out quickly. So I'm only looking at 1 second of data here at the bottom, but you can see it peaks up and then it dies out within a few milliseconds, and you end up with that smack sound or that click sound. And if I go to my cheat sheet, we would use something called wavelets or kurtosis to analyze a click sound. And the reason we would use wavelets or kurtosis is because clicks are a transient sound, and they're actually really difficult to diagnose because they're so transient. We'll explain why that is later. Transient, what we mean by transient, is something that appears very quickly and dies out very quickly. It doesn't happen over a long period of time. So this is like an impulse. This might be a keyboard click or somebody slamming a car door, for example. Things that die out very quickly. Fourier transform or traditional FFT, they do not work on transient sounds. We'll go on to explain why in a little bit, but for right now, those don't work. So we can't use the same techniques we were using before in our hoot noise to look at these transient sounds. So we have two different things we can use for something like a click. One of them is called kurtosis, which I'm going to explain, and the other one's called wavelets. So kurtosis is a statistical measure. It's something that's not unique to NVH. It exists in common statistics. And what it aims to do is it aims to quantify how peaky your sound is based on its general shape. So what I mean by that is, let's say I have some time data and it's over some amplitude, maybe voltage. Kurtosis will divide up these into different bins or classes. And then what we're going to do is we're going to count the data points in each bin and build a histogram. So for example, bin 1 has about 1 data point. So I would count across bin 1. And I would plot that in my histogram as 1 data point. Bin 2 has 5 data points. I'd plot it here as 5 data points. Bin 3 has 5 data points. And bin 4 has 2 data points. So I end up with a distribution. And really what kurtosis is trying to do is describe the peakiness of my distribution. So let's look at something like a square wave. Square waves are interesting because most of their data points are concentrated on the extremes, either really high or really low. So if I count these across, I end up with 8 data points. I could plot that. 0 data points, 0 data points, and 8 data points. And I have something that sort of looks like a bimodal distribution. This definitely doesn't look Gaussian or like a normal or standard distribution. Now let's look at where we have something that looks like an impact, something that's really sharp and peaky, but then dies out quickly with time. So I have 0 for my first bin, a high concentration of data points from my second bin, 0 from my third bin, and a single data point from my fourth bin. So I end up with something that's very peaky in shape, that's not normally distributed, that has a lot of skewedness to it, which is essentially what kurtosis is doing. It's kind of telling us how skewed our shape data is. So you could repeat this process with real signal and sort of get something, a random signal might look something more like a random bell curve. And here's the equation for calculating kurtosis. In test lab, we calculate something called kurtosis excess, which is just the kurtosis equation here. this regular kurtosis equation, but subtracted by 3. And the reason 3 is being subtracted is because it's actually normalizing it for a standard bell curve or Gaussian distribution. Just something important to keep in track of. If you're calculating kurtosis, it's this. If you're calculating kurtosis excess, you would just subtract 3. And in test lab, we calculate kurtosis excess, but the comparative values should be pretty similar. So here's our 3 classes. We have that Gaussian random distribution, which has a kurtosis of 0. It's normally distributed. We have a square wave that has sort of a bimodal distribution. So we're going to end up with something less than 0 because it's very, very gradual. And then we have something with a sharp distribution, like an impact. We end up with a positive kurtosis value, something higher than 1. So really what we're looking at when we try to analyze clicks and bumps with kurtosis are high kurtosis values. So this is something you could set for your company where you have a standard, a kurtosis value you're trying to make sure that clicks and bumps stay beneath, and you could calculate the kurtosis and see what that comes up with. So what we're really trying to do is decide, is our peaks sharper or flatter, or how is it skewed? That's kind of what we're doing with kurtosis. It's describing the shape of our bell curve. So I have a quick demonstration in test lab with that click. So I have 2 clicks. I'm going to play them for you really quickly. One is the click we heard in the beginning. And this one is another transient click. So personally, the second one to me sounds more tinny, very metallic, dies out really quickly. And if I had to pick between the two on what was more annoying, first click is less annoying than that tingy, metallic-y click. But let's see what test lab says. So I'm going to add these to the input basket. Actually, I'll hit replace input basket. And the reason that there's 2 files is because these were originally wave files, so there's a left headset and a right headset that automatically gets converted when you bring in a wave file. But they're the exact same data, so it doesn't really matter. I'll go to processing, and instead of calculating a spectrum average, I'm going to calculate some statistics. So if I were to run this, I could click run, go to my active analysis, and take a look at my statistics. So my kurtosis value for the click was about 219, and for that tingy transient, it's about 324. So it's more peaky than the click, more transient. So I would kind of agree with that. I think that that ting sounded certainly more transient than the click, and then I could accept the results and save them into my project. But I'm going to reject them for now because I don't need to save that information. Hop back over to my PowerPoint. So kurtosis is one way we can do it. The other way is with something called wavelets. So I'm going to try to describe wavelets and why we use them. So we mentioned earlier that we can't just use the FFT to do everything, and the answer to that is why? Why can't we just use an FFT like we did for our hoot to analyze these clicks? Well, we're going to try to explain that. So I have my little FFT robot, and this guy is going to be our stand-in for the FFT algorithm. He's going to be trying to figure out what the frequency is of our signal. So that's kind of his job, that's what he does. And the way he does that is he takes a cosine wave or a sine wave, something very specifically that looks like this shape, and he probes the signal with different cosines and sine waves, and then he's going to find out which ones have the highest correlation. And I challenge you to not think of the FFT just as a spectrum of the frequency content of a signal, but the correlation or the confidence of the frequencies of the signal. And I'll explain what I mean. So here we have a cosine wave, and then he's going to test it at all different frequencies and different amplitudes, and he's going to say, aha, my signal is a 2 Hz sine wave at 5 volts. And he'll give me a little plot that looks like a 2 Hz sine wave at 5 volts. And because we're very confident that this is alone a 2 Hz sine wave and there's nothing else in it, we have a sharp, concentrated peak at 2 Hz. So I like to think of these spectrums as not just a spectrum of the frequency content, but of the confidence of the frequency content. Because we're very sure of where that frequency is, it's at a sharp peak at 2 Hz. Now, what if we have something like a click or a bump, something very transient that dies out in time? Our little robot can send our signal over, He's going to try to analyze it, but he's quickly going to get pretty confused because these aren't going to align properly. And part of it is the transient died out way too quickly. There isn't enough time data for us to confidently say we know exactly what frequency that's at. So instead of getting a sharp peak, we're going to get something with a bunch of smearing in the frequency domain. He might think, hey, I think your frequency might be around 10 hertz, but I'm not sure. I'm getting a lot of information and my confidence went down. So instead of a sharp peak at 10 hertz, where we're certain that this wave was going to, go on for a certain number of time, we could say for sure that it was going to be 10 hertz. We get kind of a dipped, smeared peak, especially because our confidence went down in where that frequency was. Now, there is something special we can do. Our robot FFT algorithm has found out we can use something called wavelets. He thinks he's outsmarted physics with wavelets. So a wavelet has a pretty unique shape. It's different than just a singular frequency. It also has some type of amplitude modulation. So we have multiple frequency components of this wave. Now, instead of probing with just the single frequency sine wave, we're going to use this shape to probe our transient signal. And this shape is very unique. It does some pretty cool things for us. It allows us to analyze both time and frequency. Now, there's always a trade-off, but it is something that gives us a little more insight into our signal and it will be more descriptive, especially for these quick dying events. So for example, I'd like to take a look at this block of time here. My fixed block of time, my observation window, is a certain amount of time, and that gives me a certain frequency resolution. And what you should notice is it doesn't matter how high I go in frequency, that frequency resolution is fixed. Even if I'm looking at 8 hertz versus 2 hertz, I'm going to get the same resolution because I'm looking at the same amount of time. If I change my time, I'm going to change my resolution. But this will always be a fixed relationship. With a wavelet, however, the relationship is a little bit different. As I go higher in frequency, I get maybe more smearing in my frequencies, but I can use a shorter amount of time to analyze that data. So instead of having a fixed relationship, I get a variable relationship or a time variant relationship. And in test lab, we call this add-in time variant frequency analysis because of this relationship. And this just has to do with the fact that we're analyzing an FFT with a sine wave, which is at one frequency, and with a wavelet, which is at a couple different frequencies. So we get more of a trade-off. Now, once again, it's impossible to not have some drawbacks. So even though I can observe frequencies with a shorter amount of time at these higher frequencies, I still get a large amount of smearing. My frequency resolution is much more coarse than it is down here with my large amount of time. So that's something to keep in mind too. We're going to take a look at this in Test Lab Classic. Now if I go to Tools, Add-ins, I can scroll all the way down, make sure that time variant frequency analysis is turned on. Now I have a signal here. This is a burst signal, and to me this looks pretty transient. It's appearing and dying out very quickly within the window, multiple times, something like that. If I come into my sections, I happen to already have a segment of this data. Looks like this. So it's just a portion because I didn't want to analyze the entire thing. I'm going to right click and add this to the input basket. And if I go to time data selection, I'll click add, and then I'll go to time frequency analysis. And the first thing I'm going to do is add this segment, make sure I can see it, and I'm going to analyze it with a short time Fourier transform, which is a little bit different than a Fourier transform, but it's still using that cosine wave. I'll click calculate selected, and you can see I've got a color map, but in the high frequency range, it's not very descriptive. I don't exactly know what's going on here. This might not be the most useful thing to look at. But if I come down, I can swap my transform to wavelets. I can leave it in my 12 per octave. I'll make sure my max frequency matches my other side. I think the highest I can do is about 190 with wavelets. I'll hit calculate selected. And here now I have a much higher description of those frequencies. Before, I had blue completely at the top that showed nothing going on in that frequency range. Now I have a concentrated red zone, and I can see some of the frequency content that's going on up here. That's just with analyzing it with a wavelet versus that Fourier transform. If I wanted, I could save these to my project, but I don't need to do that, so I'm going to head back to PowerPoint. So here's my next sound I have for you. That one's a little loud. I'll play it one more time. So really quickly, we can eliminate how we would describe this sound. It's definitely not a ping. Pings are distinct, sort of like that tinny metal noise we heard earlier. Ping. Lugging tends to be lower in frequency. I can show you an example of that later. So it's really between chirp and rattle. But to me, that sounded kind of like a bird chirping a couple hundred times over the course of the duration of that sound. And in fact, if you heard that sound, I think I would be pretty worried that some bolts or nuts or something is loose in whatever machine you're working on. If I go to my cheat sheet really quick, this is a chirp sound. We can use something called tone to noise ratio and prominence ratio. These are sound quality metrics that look to quantify that high frequency pitch or chirp that's present in our sound. So tone to noise ratio is very simple. What we're doing is we're looking within a critical band, which is just bands based on human hearing. We're looking at a critical band, so some frequency level, and we're trying to find if the tone, that chirp or whatever sound, is very high above the background noise. And the reason for that is if it's not high above the background noise, we'll get some nice sound masking and we don't have to worry about that tone as much. So we're looking at that tone to noise ratio. So here's our tone, here's our band, and we're really looking at the ratio between them, the tone to noise ratio. It can be calculated based on this equation. It's calculated within one critical band, and this can be an advantage, and this can be a disadvantage. And I'll show you an example of when it's a disadvantage. We qualify tone to noise ratios as prominent, or noticeable, I will say, if the tone is 8 dB above our noise floor. I'll say 8 dB asterisk, because I'll make a note later on. But if it's 8 dB above, you can almost guarantee that people are going to hear it and that it's going to be very noticeable and probably pretty annoying, like that chirp noise was. Different noise standards have different thresholds. One of them says 9 dB depending on the standard if you're using ECMA 74 and ISO 779. This is something that you can do in Test Lab. You can calculate it a couple different ways. I'll show you the ways to do that. You can calculate it as a single value, as a map, or you can use your cursor and go through and calculate it that way. So we say that if it's 8 dB above, depending on the frequency of that tone, then we're going to notice it, be very prominent. Lower frequencies though, we give ourselves a little more room to work with. Because lower frequencies are so much harder for humans to hear, we don't really consider a tone prominent unless it's almost 15 dB above in these low frequencies. But for high frequencies, if it's really shrill, which is where chirps tend to be, we consider that 8 dB above is where we would consider it prominent. Now we have something called prominence ratio, which is very similar, but the main difference is that instead of just looking at a tone within its own band, it takes the RMS of all of the energy within a band, and then it compares it to the two bands near it. And if this energy is 9 dB or 8 dB above the two bands, then we would consider this prominent. And sometimes prominence ratio can be a better calculation depending on how your data looks. And we're going to take a look at that in a second. So here, for example, the cursor is sliding around and my prominence ratio is going up even though I'm no longer centered on the tone. And the reason for that is the tone is still within this green band, so the total energy is still high, but I'm shifting my other noise bands around, and when I do that, the ratio increases, so my prominence ratio is higher. So we consider the prominence ratio 9 dB above 1000 Hertz. The rates look a little bit different. So let's take a look at what that looks like in Test Lab. So I have my chirp. I'm going to add to my input basket. We can take a look at it too, just if I want to be extra sure that I'm showing you a chirp and I'm not trying to sell you something, here's my chirp. I'm going to go to processing, and for this one I want to make sure that I have my sound quality turned on, so sound quality analysis needs to be loaded for this. And I'm going to actually calculate both the prominence ratio and I will calculate the tone to noise ratio. Now, if I wanted to, I could calculate the maps. That'll just show me color maps of the tone to noise ratio over time. I'll do this just for fun. I'll do it for the prominence ratio too. And I'm just going to connect all of these. And more importantly, because I want to see that frequency content, I'm going to look at the spectrum map, because this is going to explain why, in this case, one of these metrics is going to be better at analyzing and catching that chirp sound than the other metric. I want to make sure my frequency resolution is set to 1 Hertz, and then I will click Run. Go to Active Analysis, which is where all my data is being calculated, and I want to look at the auto power, and I'll zoom out. And one thing you can probably see right away is that there's some high frequency content, especially around maybe 5,000 Hertz, but there's nothing that really stands out as a peaky or chirpy tone. Nothing we would expect, especially based on those graphs I showed you for tone to noise ratio. If I wanted to calculate tone to noise ratio without looking at these, I could do it just with the cursor by right-clicking Calculations. I'll turn on tone to noise ratio, and it's pretty low, 0.7 at 5,000 Hertz. And then I could turn on Calculations and go to is it prominent? And it's saying, no, it's not prominent. And you might think, well, that's not true. I can absolutely hear it. And the reason for that is because it's not standalone high within its own critical band, it's not going to appear out of the data that much. Now let's take a look at calculating it with prominence ratio. So prominence ratio is a lot higher, 12 at 5,000. And I can turn on, is this prominent? And with the prominence ratio, we get an immediate yes, this is prominent. The reason for that is because they're being calculated differently. This is looking at the total energy in this critical band compared to the neighboring bands, which in data like this is probably better for picking up on that tone. If I wanted to see what the values were just straight up, I could look at the prominence ratios. So you can see the prominence ratio of the chirp, and these signals are the same even though it calculated a left and right. And I can also look at the tone to noise ratios. So the prominence ratio, if you can see, these are the same data, so we only really need to look at 2 of these maps. But it's definitely capturing my prominence ratio much, much better than capturing my tone to noise ratio. And even here we can see tone to noise ratio is much lower than my prominence ratio. So if you're unsure, because these are so easy to calculate, you can just calculate all of them if you're trying to figure out where that chirp sound is and what you should do about it, and if it's really above your dB level, and then take a look at both the prominence and the tone to noise ratio. It costs almost nothing computational wise to do it in test lab, so I usually recommend if you're starting from scratch, you throw everything you have at the problem. I'll hit reject, jump back to our presentation. So here's another example of a sound. Play it one more time. Right away we can say it's probably not a squeal. It doesn't sound like, something high-pitched. It's not a zipper, it's not going ba-boom, ba-boom, and it's not shrill. So we're left with something really low frequency. We call this a rumble. If I go to my cheat sheet, can see what we do for rumble. And for rumble, we look at something called a roughness sound metric. So typically, if we're trying to figure out how we're going to quantify this rumble, we'll look at something called roughness. And to understand roughness, we really have to understand what modulation is first, because roughness is a metric based on modulation. Imagine, set aside, that we have 2 sine waves, one at 400 Hertz and one at 405 Hertz. If we were to add these sine waves together, maybe they're fans spinning at slightly different frequencies, so we could audibly hear them. So if we were to add these signals together, what would we hear? We would have some places where the signals are destructively interfering, so they're canceling out because they're out of phase. We get almost nothing we would hear at that point. And then we have some places where they're constructively interfering and they add and we get higher amplitude. Now, interestingly enough, these signals are 5 hertz apart. If we were to zoom out and look at the signals in entirety, the 400 hertz and the 500 hertz, and we added them together, we would end up with something that looks like this. And if you were to play this back, you would hear the frequencies, but it would be like wow, 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 wow. Something that sounds modulated. And it's modulated because of that cancellation in and out of phase, because these frequencies are so close to each other. We end up with a modulated signal. So this is something that we would hear. Absolutely, we would hear these modulations. You can hear it in the rumble. But if we were to plot these with just an FFT, our spectrum would look something like this. We would have a peak at 400 hertz, a peak at 405 hertz, and then we would have nothing at 5 hertz. There's 5 modulations per second. We can hear this, but it's not actually present in our signal. We only added together a 400 hertz signal and a 405 hertz signal. So this signal is actually not made up of any 5 hertz signal. Now, FFTs, I'll put frequency on the bottom, that's not super useful if we want to find out how our signal is being modulated, right? We can't just use an FFT. But what we can do, and the answer to this is no, what we can do is we can do an envelope of the signal, right? Instead of looking at just the FFTs, we can take the shape of this signal and do an envelope. So here we have something called the Hilbert transform. It was originally developed by a mathematician and engineer named Hilbert, and he came up with the idea of just taking the outline of the shape. So it's a mathematical equation that looks at the outline. So here's an example of a modulated signal. It has a 10 hertz modulation amplitude. So you can see the Hilbert envelope will look at the envelope of that signal. So if you were to match these up, you should see that these look like they cover right on top. And then we can take the spectrum of the envelope and we'll see where that envelope is occurring at. So in this case, it's occurring at 10 hertz modulation. So now we have a good idea of where our modulation is, even though we didn't get that with just an FFT. Now, this is a lot to say, that the reason we look at modulations is because there's 2 metrics that kind of quantify that rumble sound. One of them is called the fluctuation strength, and one of them is called roughness. So when they were coming up with a way to measure fluctuation strength they found really got perceptible to people if they were 4 beats apart. So we'll call that the beat frequency. That's the wow, wow, wow frequency. If they were 4 modulations apart, or 4 beats per second, then people thought that was really noticeable, and this curve changes as you increase in modulations. People tend not to notice them as much. It sort of dies out around 20. So we came up with a metric, we call this a vacil, which comes from the English word for vacillate, which means to waver, kind of like what a modulation is. And we decided that that was the strength produced by a 1000 hertz tone at 60 dB, modulated by 4 hertz, because that was the most perceptible. So that's what we're comparing everything to when we look at the fluctuation strength. There's another metric. You could calculate this over time. It'll tell you the fluctuation strength based on our signal. And you don't have to do this yourself. This is all done in test lab. But there's a metric called roughness. So if you look at roughness, what they found is, once again, we decided that 4 hertz beat frequency was noticeable, but it started to pick up again, and the second peak that they found was about 70 hertz beat frequency was also just as noticeable as 4 hertz beat frequency. So they came up with a different metric to quantify how to describe modulation once you get into these higher beat frequencies. Typically, roughness is used for somewhere between 20 and 300 hertz beat frequency, with that noticeable peak at 70 hertz. And because we like to make things a little more complicated in the sound quality world, instead of a vacil, which is at 4 hertz, an asper is the same reference tone, but it's at 70 hertz, because that's where it's really perceptible. So If you're like most people, you probably don't know how many modulations are in your signal. You're probably not hand counting them. And you could do a Hilbert envelope, but you could also just calculate both the fluctuation strength and the roughness and get a good idea of which one is higher, and that one will probably tell you which metric you should be using. So both of these can be used and calculated at the same time. We'll take a look at how to do that in Test Lab. So I'm going to go back to my desktop, and I'll put my rumble in. This is my rumble. Add to the input basket. Oh, actually, I will replace it in the input basket. And I want to give it something to compare it to. So I'm going to give it white noise, which is very flat. There's no modulations in white noise. There shouldn't be. It kind of sounds like a waterfall. I'll play it really quick. Maybe a bit loud even. So that's our white noise, and just for comparison, here's our rumble again. Much more low frequency with those modulations. And we'll go to processing, and I can delete all of this. And I'm going to type in roughness. Because I want a singular value, roughness has to actually be calculated off of the map. But fluctuation strength, which I will also calculate, can be directly connected to my time data. And then I'm going to click Run, and I'll go to Active Analysis, Fluctuation Strength. So here's the fluctuation strength of my white noise versus my rumble. You can see that the rumble, I'll add the run name so that it's easier. My rumble in red has a much higher fluctuation strength than my white noise, which is what I would expect, because you can physically hear the modulations, especially over time. The roughness we can take a look at. I want to make these a little bigger so I can see them. So the roughness for my, make sure I have these added onto the run name. We can be very sure what we're looking at. The roughness for my white noise, and the roughness, run name, for my rumble. We could even put them on the same scale. I'll make sure that they're both scaled to 1. And you can see that the white noise has almost nothing, no modulations whatsoever, especially in the roughness. And the rumble has a lot of modulation. The roughness develops very quickly over time. And it gets almost to 1 aspere. One other thing quickly I want to talk about is some of the other noises. I'll jump back to that sheet. So I'm going to look at shrill, and don't have PowerPoint slides. I'm just going to play the sound for you. So a shrill is something that's really high pitched in frequency. You definitely know it when you hear it. And for that, we usually qualify it with something called sharpness. That's trying to quantify how much of that sound is high frequency and how much is low frequency. So I'm going to compare the shrill to that rumble. I'll jump back to Test Lab real quick. So here is my shrill noise. That's not nice to listen to at all. And then here's that rumble noise again, just for comparison. Nice and low frequency. So right off the bat, I would imagine that the shrill noise is going to have more sharper content than that rumble. But we'll see what Test Lab says. I'm going to replace my input basket, go to processing, delete all of this, and look up sharpness. This is measured in accompanying. If you have questions about sharpness, we have a great community article on it. I'm going to leave the settings as they are, and I will click Run. And now I can come into my active analysis and see that, once again, we have left and right because this is a wave file that's split into 2. But if we just look, the shrill sound in purple or magenta is way, way higher in content than that low, deep rumble. And it's pretty consistent over time, which is what you could hear when you were hearing it. It was the high, tinny, sharp, shrill sound, maybe like a saw or something that was running constantly. And this could be very annoying over time, especially if you worked in a shop where you had to listen to it all the time. That's an example of when you would use sharpness. Now, last thing we have a mystery sound. This looks pretty chaotic, but let's just take a listen. Pretty loud and electronic. Now, if I were an engineer trying to analyze this sound, probably the first thing I would do is just look at an FFT. It's not a transient, so we could probably start there. And because this sound, I know for a fact, is going to form something cool, we're going to look at it as a color map. So I'm going to replace in my input basket, go to processing, and instead of a spectrum, I'm going to look up spectrum map. Here we go. And make sure you have the signature analysis add-in or sound quality analysis turned on for this one. I want my frequency resolution to be really coarse just because I have a good idea of what I'm looking for. And because it's not a long signal, I want my time increment to be really small. And then if I click run, I have my color map. And would you look at that? We have the Siemens logo that was a sound file, and we were able to successfully translate it to a color map by using frequency. So this signal was modulated, the frequencies changed a lot throughout it, and it changed over time, and it had to do that to create this specific word. So we could technically throw all of our sound quality metrics at it, but for fun, it's the funnest just to see it in a color map form. So that's all I had. Thank you so much for joining me today. If you have any questions on sound quality, sound measurements in general, or you just want to chat, feel free to shoot me an email at steph.nelson@siemens.com, and I would be more than happy to answer any questions that you have. Thank you, everyone, and have a lovely day.